Okay, so, do you have any questions? Yes?
For the homework for number 2, how do we go about solving this?
In what sense? Problem number 2 in section 4? What do you mean how you go by solving it? There's two graphs. One of them is the graph of f, the other one is the graph of g. Right? So the whole idea is you're supposed to pick it up from the graph. What is the limit in each point? So if you look at the graph, notice that f of 0 is 0. So what would the limit of as x goes to 0 of f of x be? 0. Right? And so that's basically the idea. So again, let me just say that again. Problem number 2, you have two graphs. One of them is the graph of f, the other one is the graph of g. There's two parts to this problem. First of all, you're supposed to pick up the limits based on whatever the picture tells you. Second of all, you're supposed to use properties of limits in the sense that you have the limit of the product is the product of the limits. Right? So for instance, if you look at part C, you have the limit as x goes to 0 of f of x times g of x. Well, as the first step, what you actually have to do is you have to say that it's the limit as x goes to 0 of f of x times the limit as x goes to 0 of g of x. And then you basically just write out whatever those two limits are. Does that make sense? Yeah? Okay. What else? I forgot to tell you on Wednesday, or I forgot to remind you, it's written on the syllabus, but I know not everybody actually looks at it. On Wednesday we have a quiz, which will be out of chapter 1. That's the idea. The entire chapter 1, yes. Today we're going to do section 5, and on Monday we're going to do section 6. The quiz will only be about half the time of the class, basically. Yes?
I didn't know how to factor number 20.
Number 20?
Yeah, the bottom.
Difference of squares. A to the fourth minus b to the fourth is the same thing as a squared quantity squared minus b squared quantity squared. Right? And so you can write it as a squared plus b squared times a squared minus b squared. And now if you look at the second part of the second parenthesis, that's also a difference of squares, and so this is equal to a squared plus b squared times a plus b times a minus b. Does that make sense? So now I guess all you have to do is just put x for a and 1 for b. Yes?
I had issues with 44, 46, and 48.
Okay. I said okay. I did 43, right? Last time. So I figured before I start section 5 today, I was actually going to do 45 just so you see how things work. And 44, it'll be kind of a variation on, like, it'll be very similar to 45. But I do have to say I'm pleasantly surprised that you actually attempted the homework already. I'm just saying, it's actually a very good approach. For those of you who haven't started it, it's a very good approach to actually start the homework now versus waiting until, Tuesday. And the main reason for that is you're most likely going to forget what I said when I said it, a week before. And, also this way you actually can ask questions as you go along with it and, can follow up. So, okay, the limit as t goes to 0 of tangent of 6t divided by sine of 2t. Sorry? Oh. Okay. So what do we do with this limit? Well, as I said, one of the things that we talked about limits, and we're going to talk more about this as we go along, is the first and foremost what you want to do is what happens when you put in 0 for t. So kind of let's assess more or less what we're looking at, and then we can decide, bless you, if we have anything to do with it or not. So if you put in 0 for t, you end up with tangent of 0, which is 0 divided by sine of 0, which is 0. So we end up with a situation of 0 over 0, right? Which we don't necessarily know what to do with. So what we're going to do is we're going to do the following. First of all, as it's customary, here, I'll actually come down here. As it's customary with trigonometric functions, and you'll see this later on, sine and cosine are basically the main two functions that we deal with, right? Tangent is basically a combination of sine and cosines. So is cotangent, so is secant, so is cosecant. And so the idea is, if I have anything involving tangent and sine, or tangent and cosine, or anything else, the first thing to say is, how about if I express everything in terms of sines and cosines? So we're going to have sine of 6t over cosine of 6t, all divided by sine of 2t. Okay? Which is the same thing as the limit, as t goes to 0, of sine of 6t divided by cosine of 6t times sine of 2t. And so now the question is, what do we do next? As I said, 45 is very close to 44, because if you just take out this cosine, you'll have exactly the same situation as you have in 44, right? Just different numbers. Yes?
Oh, wait. So you have a fraction divided by a fraction. So the denominator you can move down.
Mm-hmm.
The denominator of the top fraction moves down to the bottom fraction.
A divided by B, all divided by C divided by D, is equal to, and I probably should have used a little more space, A divided by B multiplied by D divided by C. Right? And so the idea is, if you look here, you have B times C in the denominator, which is the same thing as the B drops down, if you want to think about it in those terms. Okay, so then what do we do next?
We try to take the numbers out.
How?
You take them outside the...
Under no circumstances you can do anything with the arguments of this. You cannot take numbers out, or you cannot take letters out, or anything else. On the same token that, and I'm hoping everybody knows this, if you look at the square root of 6t, that's not 6 times the square root of t, right? And so, if this doesn't work, then neither should the other one work. Does that make sense? Sine is an actual function. It's like the square root, which is also a function. So whatever you have past sine, that is the argument of the function, and you cannot do anything to it unless you actually apply some double angle formulas or some other trigonometric tricks you can, use. Okay, so now what should we do here? Well, let's do the following. I'm going to have the limit as t goes to 0. And I'm going to write this in the following way. So what I'm going to do is before I actually get there, I'm going to multiply and divide by 6t. Why can I do that? Well, because t is not 0, so I'll just multiply by a particular form of 1. Okay? So I'm going to separate this into three parts now. I'm going to have 1 over cosine of 6t multiplied by sine of 6t over 6t multiplied by 3 times 2t divided by sine of 2t. And apparently I keep going higher and higher. Is this making sense? Maybe not necessarily why I'm doing this, but do you see the equality? Yeah? Okay, now what is the limit as t goes to 0 of 1 over cosine of 6t? Since everybody seems to be like a deer in a headlights, let's do this. So using properties that we talked about last time, the limit of a product is the product of limits. Okay? So now, what is the first limit? Well, what is cosine of 0? 1? Okay. What is the second limit?
1.
1. What is the third limit? 3. So what is my answer? 3. Does this make sense? Yes? Yes.
How did you get from the, like, down
I know that. So I know that. Here, I'll put it over here. I know that the limit as y goes to 0 of sine of y divided by y is equal to 1, right? Regardless of what this y is. Now, because I can't actually take the numbers out, I know that the only way I can actually deal with this is actually to write it as sine of 6t over 6t. And similarly, I have sine of 2t, and so I know that I can have a 2t, or I need a 2t there. Is that answering the question?
Yeah,
Kind of. It's a trick, basically. This is why I figured I'm going to do one of these so you can actually see how the trick works. Because you have sine over sine, keep in mind that sine of y over y, this limit is 1, which means also y over sine of y is also going to be 1, right? Because it's just going to be 1 over 1, which is still 1. And so if I have sine over sine, I know I can actually manufacture these t's without actually losing anything. Yes?
Can we expect anything this complex? Some tests and quizzes?
Oh yeah. This is not complex though.
That's great.
Sorry, but this is actually not. It'll get a lot more complicated.
What about next week's quiz?
Well, yeah.
I mean, because there's similar problems from the homework. Like, I think 44 or 46 were a lot more simple than that.
44 is basically the same as this. The only difference is you have a tangent to begin with. That's, the only difference. Right? And 46 is actually very simple. For 46 just comes out directly out of property, whatever did I say? I think I called it number 6 or something. The second to last property I gave you as far as laws of limits. Otherwise, if you want to use the textbook, or if you remember the ones in the textbook, it will be number 6 in the textbook. So clearly then it's not my number 6. Anyway. Okay. Questions? So since you asked me about 44, did you know how to do 34?
34? Yeah,
What's the answer?
I got does not exist.
Okay, that's a good answer.
But it was weird because it wasn't like any of the other problems, because I ended up getting 0 over 0, but because it's an absolute value, and we're looking at the value of negative 6, it's just going to be 0 over 0 no matter what we do.
Yes, but it's...
The better way to say that.
Yeah, it is going to be 0 over 0, but you have to simplify it. So how did you get that it doesn't exist?
Well, I plugged in negative 6 for the absolute value, but then for absolute value you can also plug in positive 6, but that has nothing to do with the limit.
Well, you have to take a little bit less than 6 for the first one, and a little bit more than 6 on the second one.
Exactly. So let's look at problem 33. It also deals with absolute values. The key idea is, as it turns out, for this particular problem in particular, putting 3 in 4x is not going to change anything. But the idea, as far as absolute value problems are concerned, is we're actually going to look at it from two different perspectives. We're going to look at x going to 3 minus, and then we're going to look at it as x going to 3 plus. And that's where we actually get the fact that it doesn't exist. Because if you come from the left on 34, you'll actually end up with minus 2. And if you come from the right, you'll end up with positive 2. Which means the two side limits don't agree with each other. Is everybody understanding what I'm saying?
Yeah.
Okay, so what is the limit coming from the left? Well, if it's 3 minus, maybe I should come down here, come to the side over here, and ask you what's, by definition, the absolute value of x minus 3. It's x minus 3, if x is bigger than or equal to 3, and if it's 3 minus x, if x is less than 3. Right? Or the negative of that, right? The negative of x minus 3, which is just 3 minus x, right? Okay? And so I have 2x plus 3 minus x. So now doing the algebra, I'll have 6 plus 9 plus 3, that's 9, minus 3, that's 6. And then if I come back from the other side, I have 2x plus x minus 3. Which is going to be, now again, 6 plus 3 is 9, minus 3 is again 6. Since they both agree, then my original answer is that the limit is in fact equal to 6. Does that make any sense?
You can plug it in first, you can check it.
Sorry?
You can plug it in first, you can check it.
Plug it in first?
You just need to check it.
Yeah, well, for this particular problem, because there's no restriction, you'll actually be able to just put in 3 and it works. But if you look at 34, it won't. You have 0 over 0, and so the only way you can actually simplify that, I'll just give you one particular hint about 34. I pretty much solved it for you at this point, but one particular indication is example 7. So if you're in doubt of how exactly to approach it, look at example 7. And it'll be solved identically as this example 7. Okay? All right. So, any other questions? Alright, so today we're going to talk about section 5, which is actually dealing with continuity. And there's two ways of looking at continuous functions, and we're going to define what a continuous function actually is. There's actually a very nice graphical representation of a continuous function. And we're also going to be looking at the actual definition. So the actual definition says the following. Well, actually, let me say first the graphical definition, because it's a lot simpler. What does it mean for a continuous line? Do you know? What would the English language tell you if somebody tells you draw a continuous line? goes forever, okay? One that doesn't, so I'm interpreting that to say that it's not interrupted, right? It's continuous, right? You put the pen down and you never lift it, right? That's what a continuous function is. Okay? That's basically the idea. So graphically, if the graph doesn't have any breaks in it, or any jumps, or any holes in it, then your function is continuous. Okay? Now, that's not necessarily sufficient. Why? Well, because, as I said last time, and I think I said it in the past as well, we're actually going to try and graph functions as time passes. So sometimes you don't know what the graph of the function is, so how can you tell if a function is continuous or not if you don't know what the graph is? And so, guess what we're going to use to figure out if a function is continuous or not? We are not allowed graphing calculators. So what else? Well, the only thing we've learned so far is limits, right?
Derivatives.
We haven't learned derivatives yet.
Is that chapter 2?
That is chapter 2, yes. So a function is continuous at a number a if the limit as x goes to a of f of x is equal to f of a. Sorry? I'm sorry, say that again?
There pretty much is no limit. If it's a continuing line, how can we...
No, you're looking at a point. So,
The whole, no breaks, no nothing. How is there a limit?
well, because I mean we've done these problems in the past, right? If you think about previous problems, we said the limit as x goes to 2 of 2x minus 3. What is it? 1. What's the graph of 2x minus 3? It's just a straight line. There's no holes, there's no breaks, there's nothing, right? Yet the limit exists. Right? Because we're looking at that particular point. There's 3 things that you actually have to take into account when you look at this. I said it verbally, right? That there's no holes. Well, you can break this up into 3 parts. First of all, the right-hand side says f of a. That means that the function's in fact defined at a, right? Because otherwise I can't talk about f of a. Second of all, the left-hand side says the limit as x goes to a equals f of x. This means the limit exists, right? And the third part is the fact that the limit is actually equal to the function. So if you think about what I said verbally as far as the graphs are concerned, right? There's no jump. Well, if there's a jump, clearly the limit doesn't exist, right? So how can it be equal to the value of the function, right? Second of all, I said no holes. Well, at holes, limits exist, but the value of the function may or may not actually exist there, and more importantly, it's not equal to the value of the limit. Is that making sense?
What?
Well, keep in mind. Okay. So 3 parts. Number 1, f of a is defined at a. Number 2, the limit as x goes to a of f of x exists. And number 3, the limit as x goes to a of f of x is in fact equal to f of a. So now I'm going to say the following. If either of the 3 parts is not satisfied, we say f is discontinuous at a. Okay? So now, the first one we said f of a is not defined at a, right? So let's come up with an example that satisfies that the limit exists, but f is not defined at a. Well, the simplest example, graphically, is that. If this is a, and this is L, then the limit as x goes to a of f of x is equal to L, but f of a does not exist because it's not part of the domain. Does that make sense? Yes? Okay. Give me an example of a function that satisfies second property but doesn't that satisfies the first property but it doesn't satisfy the second, which means function is defined at a but the limit doesn't exist. That would be a very lovely example, right? This is L. The limit as x goes to a of f of x does not exist, but f of a is in fact equal to capital L. Is that making sense? Everybody understands this?
Oh, wait.
Yes.
Wouldn't there be an open dot on the bottom line and a closed dot on the top line?
Why? Doesn't matter.
Doesn't matter.
I just put it on the bottom, but it doesn't matter where you put it. All I'm saying is, I mean here, if you so choose, I can have it that way. I would have to change this because it's not L anymore, but nonetheless, the point is, function still exists, value of the function still exists, but the limit doesn't. So now, can you come up with an example in which the two conditions are satisfied, but the third one is not? Which means the value of the function exists, the limit exists, but they're not equal to each other.
Use the first graph, but for a different point.
Bingo. Use the first graph and just add the point. Is that making sense? The limit is over here, but the value of the function is over here. They're not equal to each other. Hence, as you draw it, you basically have a discontinuity, right? You have to lift your pen to continue drawing it. Does that make sense? Yeah? Okay, so let's say, let's label these. I'm gonna label this M, I guess, and I'll label this L. This is A. So the limit as x goes to a of f of x is equal to capital L. F of a is equal to capital M. Does that make sense? Okay. As it turns out, we witnessed two types of discontinuities. There is a third type that we haven't talked about yet. The two types of discontinuities we talked about, one of them is called this one. This is called the removable discontinuity. It is removable because the limit exists, and all I have to do is basically define the function to be, L at that point, and my function becomes continuous. And then the other type of discontinuity we talked about is a jump discontinuity, which is this particular case. And the name suggests it all. The value of the function jumps, or the graph jumps from one point to another. Does that make sense? Yes? So, let's see. If I name this A and this B, so I don't have to do it again, I have three types of discontinuities. A is a jump discontinuity. B is a removable. And C is called an infinite discontinuity. And we haven't actually looked at an example of an infinite discontinuity. As it turns out, the infinite discontinuity fails both first and second. Okay? Remember, we looked at examples that either fail the first, but the second one held. We looked at one that first one held, second one held. So far, so good? So which would be an infinite? Well, I'll give you an actual example of a function. F of x equals 1 over x. Do you know the graph of 1 over x? It looks like that. 0 is called a infinite discontinuity. And the name kind of suggests it all. Why? The point is, as x gets closer to 0, your graph actually shoots to infinity. That's basically the idea. That's why it's called an infinite discontinuity. Okay? Is that making sense?
Wait, is that the only example? Or is there more?
Oh, on an infinite amount of examples.
Where it just doesn't touch 0.
Any rational function will have an infinite discontinuity. Any vertical asymptote is an infinite discontinuity. Yes, 0 is a vertical asymptote. I am good. I answer questions before they're even posed. Okay, questions. Does this make sense? Kinda, sort of.
We'll need some more.
Okay, so let's talk a little bit about what I'm going to do is I'm going to do the following. Let's give another definition. A function f is continuous to continuous from the right at a if the limit, what would you guess, by the way? How would the function be continuous from the right?
X goes to A minus.
That would be from the left, right?
A plus.
A plus of f of x equals f of a. As an example, just think about can't seem to be able to fill that up completely. Does that make sense? Yeah? So now the idea is that the limit from the right has to exist. The value of the function has to match the limit from the right. Does that make sense? Okay, similarly, it's continuous from the left. F is continuous from the left at A if the limit as x goes to a minus of f of x is equal to f of a. Do you want an example, or same thing with the bubble on the bottom, right? I guess bubble would assume it's empty.
Well,
Yeah, the
same example. Same picture, though.
Same picture.
Why is that? Why does the dot have to be on the other side?
because this is the limit from the left is here, and that has to match the value of the function. Here, the limit from the right had to match the value of the function.
Oh.
Okay? Alright, so as it turns out, we're going to have some tools to deal with as far as continuous functions are concerned. So we don't have to actually compute these limits every single time, every single situation we're in. But first of all, let's do another definition. It says the following: a function is continuous on an interval I if it is continuous at every point in I. So, as it turns out, we're pretty much in luck in general, because think about graphs of polynomial functions. Right? Think about a quadratic function or a linear function, right? You just have a straight line. A quadratic, it's a u or an n based on whatever the value is. If you look at a cubic, it kind of looks like a, I don't know, snake. The key idea in all of these is that the graphs are all continuous, which means every polynomial function is continuous everywhere. Does that make sense? Why? Light show. Why? Well, think about previous section when we talked about the direct substitution formula or theorem or whatever it was called. Right? The idea was if it was a polynomial or a rational function and the value was in the domain, the limit was just the value of the function. Right? Well, that's the definition of continuity. Right? Which means a polynomial, a rational function, root function, trigonometric function, they are all continuous on their domain. So let's write that out. I'll dot this a theorem. Any polynomial, rational, root, or trigonometric function is continuous on its domain. Does that make sense? Yes.
So what you're saying is there's no open values on the water problem.
On their domains.
On their domains.
But you have to be careful with that. On their domains.
Can you elaborate on that, honestly?
Well, f of x equals x squared plus 2x plus 1 divided by x plus 1. It's a rational function, right? When is f continuous? F is not equal to -1, right? If you want a picture, your function looks like that, right? Keep in mind, f of x equals x squared plus 2x plus 1 divided by x plus 1, which equals x plus 1 quantity squared over x plus 1, which equals x plus 1 as long as x is not equal to -1. Does that make sense? And so where is f continuous? Everywhere except at -1. Why? Because that's the domain of f. And we said f, all trigonometric, root rational, and so forth are continuous on their domain. Does this make sense? So, is this making sense? So, it doesn't necessarily have to be like a vertical asymptote. It can very well be a hole, because you could have a situation of this nature, right? Is everybody understanding this? Obviously, if I look at f of x equals 1 over x squared, what is the domain of f of x? Since the domain is everything except 0, then f is continuous everywhere except 0. Graphically speaking, what's the graph of 1 over x squared? Just looks like that, right? So visually you can see that it actually is smooth. I mean, it's actually uninterrupted anywhere except at 0, right? Yes?
Where are we getting with this? Because it's not entirely continuous. It's just continuous in all the areas except the point, except on the domain. Is that what we're finding out here?
We're trying to figure out where functions are continuous, yes.
Okay.
Because as we'll find out, I guess probably not next week, but the week afterward, actually maybe next week as well. Functions have derivatives only if they're continuous. And we're going to talk about what derivatives are. But before that, we need to figure out when functions are continuous, because as you can see, when functions are not continuous, they can behave quite odd. I mean, the above example is relatively simple because that's called a removable discontinuity. I can basically define the function to be 0 at -1, and then at that point on, I have a continuous function, I can proceed. But if you look at 1 over x squared, at 0 it shoots up at infinity. And so I don't want to be anywhere near 0 because it just, it explodes on me. Okay? And so that's basically kind of like a few things that we're trying to gather here. Okay, so let's see. Should we maybe skip and go and look at some of those things here? Okay. What is your homework? We have 4, 6, 10, 14. Okay, how about I do 5 so you kind of get a feel for what 6 is. It says, sketch the graph of a function that is continuous everywhere except at x equals 3, and it's continuous from the left at 3. So, any thoughts? It's continuous from the left at 3, which means, remember what continuity from the left means. So, continuous from left at 3 means the limit as x goes to 3 minus of f of x is equal to f of 3. So I made too many straight lines, so let's make it a little more interesting. Does this make sense?
Well, continuous from the left, that means going left, right?
That means from the left, you're going from the left, you're coming from the left to 3.
Okay, that's continuous.
So from the left coming to 3, you have your graph has to end in the value of the function. No, I just said I kept drawing them straight, so I should be a little more creative. Actually, nobody stops me from having something like this, and maybe I should have done this in the past. The point is, it can be jagged. It doesn't have to be smooth like I've been drawing all of them. This is also continuous. Is everybody understanding this? key idea is how I drew it. I basically put my pen here and I never lift it up, right? Doesn't matter that I actually made very sharp angles. Everybody understands? And we'll actually find out what happens at these sharp angles is that there's something interesting going on there, but we'll find that out later on, in the sense that it has something to do with derivatives. Okay, so this is number 5. What else? How about we do 15? We have f of x equals 1 minus x squared if x is less than 1, and it is 1 over x if x is bigger than or equal to 1. We are supposed to explain why the function is discontinuous at a equals 1. Okay? So, when you're asked to say why is f discontinuous at 1, what you're actually asked is to figure out which of the 3 criterias are not met. Is everybody understanding this? Right, because you're supposed to explain why it is discontinuous, so you basically have to say which case you're in. So, how do we figure things out? First of all, I should point out one thing. Is this function continuous before 1? So, is f continuous on minus infinity to 1?
No.
Why no?
Yes, there's no 0.
I said on interval minus infinity to 1. On this interval, f of x is 1 minus x squared. Right? Yes? Remember, piecewise functions. X being less than 1 sends me over there. F is this function on that interval. But what is this function called? Polynomial. What did we say about polynomials? They're continuous everywhere, right? So this function will be continuous here. Does that make sense? How about, so the answer is yes. How about, is f continuous on the interval 1 to plus infinity? Well, f of x is 1 over x on that interval, right? What's the domain of 1 over x? Can't equal 0, right? Everything outside of 0? Well, clearly this interval is outside of 0, right? So, yes. Does this make sense? If you don't believe me, let's think about the graph. What is the graph of 1 minus x squared? Looks like that? Sorry.
Yeah, it's on the axis.
Right? What is the graph of 1 over x? So this was an empty circle. Does that make sense? Again, this is part of graphing piecewise functions to kind of get a feel for things. So, what should our conclusion be, by the way, about why is f not continuous at 1? They're not going to equal each other. Which one of the 1, 2, or 3 is actually going to not be satisfied? What is f of 1? What is f of 1? 1. Everybody sees that f of 1 is 1? Yes or no?
Yes.
Because I heard 0.
You said 0.
I don't know, somebody. Do you understand why it is not 0? the equality sign resides on the second branch, which means that 1, I'm looking at 1 over x. Yes? Alright. What is the limit as x goes to 1 minus of f of x? Well, if you look at branches, I'm trying not to show you the graph too much because you might not necessarily know how to graph things. Otherwise, like for instance, 14 is 1 over x minus 1. Do you know how to graph that?
No.
Okay, so if you come back here, the limit as x goes to 1 minus means x is less than 1, means I'm in the case of 1 minus x squared. Means if I come down here, this will be the limit as x goes to 1 minus of 1 minus x squared, which is 0. And if I come from the other side, the limit as x goes to 1 plus of f of x is the limit as x goes to 1 plus of 1 over x, which is equal to 1. This means that the limit as x goes to 1 of f of x does not exist, which means we're not satisfying the second criterion we discussed, right? We showed that it satisfies the first criterion. It doesn't satisfy the second. Clearly, by the way, if it doesn't satisfy the first or the second, it'll never satisfy the third, right? That would be pretty obvious. Third says the limit is equal to the function, the value of the function. Well, if the limit doesn't exist or the value of the function doesn't exist, how can they be equal to each other? Right? Okay. What else do we have?
Oh wait, is this the kind of answer you expect for 15?
For 14. For 14, you're supposed to explain why the function is discontinuous, and we just explained the limit doesn't exist.
Okay, I mean, could we leave it at like if f continuous, like, and then we answer yes, like if you scroll up?
Well, actually, that was not part of the problem.
It wasn't.
You were only asked to say why the function is discontinuous at 1. This was actually bonus. I actually just wanted to give you a little bit of a perspective on how to figure out when the functions are continuous or not. Okay? So technically for your, when you do 14 and 16, you don't have to do this. Your only focus is at x equals 1. That's it.
So the bottom part.
Yes. Okay? Alright, so let's see. How about 27? It says the following. F of x is equal to x squared if x is less than 1, and the square root of x if x is bigger than or equal to 1. So the reason I approached problem 15 in the way I did is because on problem 27 and problem 28, which you actually have to do 28 for homework, and I've seen this long enough on exams to know that you kind of have a tendency to forget to say that, you're actually asked to show that this function is continuous everywhere. Okay? So how do we do that? Graphing is not part of it. Remember, graphing, the only reason why I brought graphing into it is because it gives you a very nice perspective on things. But remember what the definition of continuity is. We actually looked at the limits, right? Not the graph. We talked about the limit being equal to the value of the function. That was the actual definition of continuity. Yes?
1 squared and square root of 1.
Sorry?
This is 1 squared and square root of 1 is equal, so it's what's
What is that actually saying?
that they get the same point.
So what you're saying is that that shows that f is continuous at 1. The problem said, show that f is continuous everywhere. And this is what people do. This is why I said, this is actually the most common mistake. This is one of the problems that I usually put on tests. And usually the answer is exactly what you just said. Well, 1 squared equals the square root of 1, f is continuous. That only shows that they meet in the same spot, which means it's continuous at 1. This is why I said I did this to kind of give you an indication of the future. Well, immediate future. There's different types of futures. It depends on how you want to look at it. Okay, so if x is less than 1, what happens? What is the value of f of x? X squared. Is f continuous between minus infinity and 1? Why? Polynomial, right? And so f is continuous on minus infinity to 1. Does that make sense? Okay?
He wants to explain that part.
Well, you have to. The whole point is you're trying to show that f is continuous everywhere. Okay? The fact that you're looking at 1 is nice and it's good. But the idea is you have to acknowledge the fact that outside of 1 you have these so-called elementary functions, and you know those are continuous. Okay? Because I can come up with a function that you don't necessarily know if it's continuous or not because we never talked about it. Okay? For instance, e to the x.
E to the x.
Mm-hmm. By the way, if you don't remember logarithmic functions that much, we'll talk about it extensively. Okay, if x is bigger than 1, f of x is the square root of x.
Yes.
And so this is a root function, right? Continuous on its domain. The domain of square root of x is anything above 0. 1 to infinity is clearly in that interval, right? So this is root, is continuous on 0 to plus infinity. So f is continuous on 1 to plus infinity. Okay? Notice I'm not necessarily being very, very detailed in my description, and you don't necessarily have to be very detailed in your description, but you just basically have to make sure you say enough stuff that somebody that reads it understands that you understand things. As in, it's a root function, you know that it's continuous on the domain, so you can proceed on. Okay, so now we come to your point. You have a question?
Yeah, wouldn't you use a closed bracket for the ones and greater than?
Well, but I don't know what happens at 1. That's the point. See, notice I actually just said x bigger than 1.
Oh, wait.
Isn't that problem?
Isn't that the problem?
What?
Just explain it too much.
You mean this isn't the answer?
This is the answer. But I still have to deal with 1. The key idea is, yes, you could probably include 1 in here, but then I would have actually had to start with an equal sign over here. But see, the problem is the fact that f could be continuous on the closed and the open would not necessarily mean that it's continuous everywhere. The ends actually have to meet. Does that make sense?
But it's not one.
So now we have to deal with x equals 1. So the idea is the limit as x goes to 1 minus of f of x is equal to, should I go into the details and write what the function is at that point? The limit as x goes to 1 minus of x squared, which is equal to 1. The limit as x goes to 1 plus of f of x is the limit as x goes to 1 plus of the square root of x, which is again equal to 1. Both of these mean that the limit as x goes to 1 of f of x is equal to 1, which happens to be f of 1. Okay? So we showed that f of x is continuous at 1. We showed before it's continuous in the other part, and so It's continuous everywhere. Does this make sense? Yeah. Okay, let's see. What time is it? The intermediate values theorem says the following. By the way, as a general rule, you will be tested on a little bit of theoretical concepts here and there, in the sense that when you look at your test, you'll probably have a question that will actually ask you to state a theorem. And those usually will be the word theorems, as in theorems that have names. For instance, at some point in time, we're going to talk about the fundamental theorem of calculus. And it's a little funny because every single time I teach Calc 2 or Calc 3, half my students have no idea what the fundamental theorem of calculus says. Yet, what is the title of the course? Calculus. The theorem is called the fundamental theorem of calculus. You would assume that it's fundamental that you know it. So anyway, this would be the first actual word theorem, and we are not necessarily going to use this that much, but it actually gets used a lot in proofs of other things. In the next chapter, we're actually, I guess, not the next one, but in chapter 3, we're going to talk about Rolle's theorem, and we're going to talk about the mean value theorem, and those are actually theorems we use, and you'll actually have those in the exam, in the sense that you're supposed to show that a function satisfies the particular value, properties of those, and so it will definitely be to your benefit to know them. Yes. Study guide? Yeah.
Like something you can show us with study form?
Yes. For the quiz, I'm not going to give you anything. For the quiz, the one thing I would show you, I would focus on would be homework. If you know how to do the homework, you should be fine. And for the quiz, the only reason why I have a quiz next week is so people don't slack. First exam is set up in week 6. That's 6 weeks into the semester. If I let you not have a quiz before week 6, chances are you're going to forget everything that happened in the first 2 or 3 weeks of class. And so this is kind of like, it's only worth 50 points, which basically means it's like 5% of your grade. It's like the equivalent of basically 3 homework sets. And so the point is to keep things refreshed. And so I will only focus on the homework. I'm not going to ask you any theoretical ideas at that point. I'm just going to basically ask you to do problems. And besides, it's only going to be like 30 minutes. And for the exams, what I usually do is I actually come up with a kind of like a, I guess, study guide, if you wish. I just come up with a bunch of problems that you can play with at home. And what I usually do is I pick, and you can more or less see this when we get there. I usually pick the even problems from the book, or I go to the chapter review and pick them up. And so basically, if you do that, plus if you know how to do your homework, you should be well prepared for the exam. You will find out that in general I have this knack of putting homework problems in tests and quizzes. So, that being said, I talked to my grader, and I guess you're supposed to give me the... anyway, I'm going to try and get the homework back from him on Monday. We'll see if that actually happens or not, just so you actually have a second homework as well before the quiz on Wednesday. Yes?
Is our grader Jason?
Yes.
Really?
Yeah.
Well, no, I know Kevin. And I thought he was our grader, and he thought he was our grader.
Kevin is my grader for my other section of Calc 1. Jason is the grader that grades every single online course. So if it's an online course, then Jason's grading it.
But this is not, so. I thought online course is a course you take from there.
There is a component to it. You can't take this class online. But if you're not an UCCS student, like for instance, I have a few students who are high school students or students who are actually from out of state. Actually, they can take the course online. They get the video. What the benefit that you get for this particular feature is that all these lectures are actually recorded, which means you can go a week from now, if you don't remember what I said at some point, and actually relook at the lecture.
You can pull these notes off your page.
And you can also pull out these notes. Yes, they're not on my website. They're actually on eCompanion. Or you can go to the Math Archives. Are you familiar with the Math Archives? I said it at some point.
Right after we were leaving yesterday.
If you go to the Math website, on the left-hand side, there's something called Video Course Archive. If you click on it, it'll give you the archive for all the courses that were ever taught online at UCCS. It starts from summer 2005. And if you see the top one there is Math 1, I guess 1350. I'm still not used to calling it that way, but anyway, you can see it there. If you click on it, you have to register to actually watch them. But anyway, not register, but it asks you for name and email password, email. So, anyway, okay.
So lecture notes are on eCompanion, and then if you want to watch videos on the Math Archive. Actually, both.
Yeah,
The videos are on
The lectures on eCompanion. Okay.
Since you're asking, let me show you. That's how it shows up. This is the video. That's the notes. So whatever I write on the tablet shows up here as a PDF file. So that would be the notes from last time. A word of caution. This does not mean you shouldn't come to class. It actually is a lot better if you do come to class, because if you have questions, you can actually ask them. That's number one. Number two, also, if you have a tendency, I don't know how you watch necessarily TV or you look at things online or movies or something. It's not like you really dedicate your full attention to things. So, you might have a tendency to start the lecture and then say, I'm going to go get a snack. So what if I forget, if I miss 5 minutes or whatever the situation may be. Or, somebody calls you, you pick up the phone and the lecture keeps going, and then you're going to lose a lot of the information. And so, you should only use this as an external help later on. If you want to review things, or, if you think that you didn't take very good notes and you want to review things and so forth, but I would not recommend not coming to class, because as I said, you can easily let things slide. Okay, suppose that f is continuous on the closed interval AB, and let n, capital N, be a number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the open interval AB so that f of c is equal to capital N.
F of c equals n.
Capital N. Yeah, the original capital N that we defined here. It looks very wordy. Do you know what it means? What it does? What is this theorem actually saying? Well, it actually says something very interesting. The function is continuous on a closed interval, which means, let's see. Let's say this is A, this is B. Should we make f of A less than f of B or bigger than f of B?
Bigger.
Bigger, okay? This right here is f of A. This right here is f of B. Pick some random n between f of A and f of B. So let's say this right here is capital N. Okay? Can you draw a continuous line starting at this dot, finishing at this dot, without crossing the red line? That's what the intermediate value theorem says. It says there's some point between A and B in which the value of your function will cross the red line. And don't think that you're going around, because this is infinite. Besides, if you go around, actually if you go around, it's not a function. Right?
Why is it not a function?
Because it doesn't pass the vertical line test. Does this make sense? Do you understand what I'm saying? As you said, as I said, the theorem might actually look a little more cumbersome, you know, in words and everything else, but it's actually very simple. It's relatively simple in the concept. I gotta go from point A to point B. I have to cross at some point this line. There's no other alternative. Now, the one thing that it does say, and you should be a little, you know, careful with this, is the fact that it says there exists a number. It doesn't say it's unique. Which means technically my function can cross that line about 50 times. Do you understand? What it says is it has to cross at least once. Why? Because it's continuous, and that's the key idea. The key idea is the fact the function is continuous, which means the line cannot be interrupted. Okay? That being said, the last problem you have to do is problem 38. It says use the intermediate value theorem to show that there is a root of the given equation in the specified interval. Okay? Would you guess how to use the intermediate value theorem to show that?
No.
What is the property of a root? How do you come up with roots? First of all, do you know what a root is? So for instance, if I look at problem 37 on page 55, I have x to the fourth plus x minus 3 is equal to 0. And the interval I'm looking at is the interval between 1 and 2. Okay? So how do I know there's a root in between that? This is an interval, not a point, right? The key idea is the following. Roots, how do we represent roots graphically? What happens on the graph when you get a root? So if I say f of x is equal to x to the fourth plus x minus 3, no, we're not talking about square roots, we're talking about zeros of a function. The roots of a function are the same thing as zeros of a function. For what values of x is that equal to 0? That's what a root is. What does it mean graphically that f of x is equal to 0? It means that the graph is going to cross the x-axis, right? Is everybody understanding this? So what does that mean for our intermediate value theorem? Well, if I put in 1 in for x, and then I put in 2 in for x, if the values of the function have opposite signs, what does that mean? F of 1, and the numbers are relatively easy to fix, right? F of 1 is just 2 minus 3, which is minus 1. F of 2 is going to be 16 minus 1, which is 15. Which means I start over here, I have to end up over there. How do I get there? I have to cross the x-axis, right? Which means I get my roots. Does that make sense? Is everybody understanding this?
Yeah.
So the only thing you have to do is you have to figure out if your signs are opposite.
Yeah. So for the problem, you're just showing that it crosses.
The only thing you're showing is that it's crossing.
Yeah.
Yes. And how do you show it's crossing? Well, f of 1 is minus 1, so I start down here. F of 2 is 15, so it's over there. My function is a polynomial, which means it's continuous. I have to come from here to there somehow. I have to cross the x-axis.
So the same n is over x-axis.
Now, when you take your calculator, when you take your graphing calculator, and you put in that particular function in there, and you say, find me a root, do you know what your calculator does? This.
Can you tell us a shortcut, or like what not to do?
No, what I'm telling you is, because you might ask yourselves, like for instance, we look at the intermediate value theorem, you're saying, okay, fine, what exactly is the real application of this? The real application of this is that your calculator is actually built to do this. How else do you think it actually solves it? It actually approximates the solution by getting closer and closer. So what it does is, for instance, you look at the interval between 1 and 2, and you say, okay, I have a root because the signs are different, right? What's next? How about if I halve the interval? Where is my root? It's going to be in this half or in that half. And I keep shrinking the interval until I actually get to a point. That is what your calculator is actually doing. And I didn't say you should use a calculator. All I'm saying is that's, I'm just basically showing you why, because sometimes you don't really necessarily realize why mathematics is actually helping sometimes. So, have a good weekend. I guess I took back the 2 minutes that